Hello scholars, welcome. Today we are going to get into a bit of history for how we think about the natural world, for how we think about how our Earth functions, what drives geological processes, and the prevailing idea, the theory of plate tectonics states that the surface of the Earth is covered by large, rigid tectonic plates that move around relative to one another at plate tectonic boundaries. Now this explains why mountains are where they are, why we have ocean basins, the processes of earthquakes and volcanoes and Earth surface processes. It's an awesome theory that really helps us understand how our world works. But that theory is relatively recent, formalized within the last 70 years or so, the 1960s. Before that, we had the idea of continental drift. Now, the continental drift hypothesis was a radical new view on geologic processes, and it was proposed formally by one individual, Alfred Wegener. And this is his story for his continental drift hypothesis. So, our objective for today is to explore the concept of continental drift proposed by Alfred Wegener. He was German, so that W is a V sound. And then look at his 4 supporting lines of evidence. So why don't we get right into it? Alfred Wegener, here he is on the left. He's all bundled up because it's cold in his expeditions to Greenland. He was an explorer. He was a weather guy. He was into the atmosphere, but he was also a vehement reader and learner and interested in science, in what was going on in current times. So you could call him an all-around scientist who studied in weather and climate. I'm just going to get his name up here. He got real interested in geology, reading some papers about fossils, and started to think a lot about the formation of continents and the oceans. What a question, right? Where do continents come from? Where do oceans come from? And how do they change through time? So he developed some ideas on this. He wrote a book that was published in 1915 called The Origin of Continents and Oceans, and it changed the world. Actually, it didn't. That was a hint of sarcasm. It didn't change the world. People didn't believe him. Even though he had really good evidence, it was too radical a view at the time. So let's look at what he was proposing. So first proposed in 1912, he wasn't the very first person to ever look at the continents and go, I wonder if these continents were all together at one point. Nope, hundreds of years earlier, Alfred Wegener actually was the first to propose that all of the continents looked like they fit together, but Alfred Wegener was the first person to not only state that, but to state 4 lines of evidence for this idea of continental drift, that Earth's continents move over time. They drift across the surface of the Earth relative to one another. He postulated that at some point in Earth's history, all of the continents had been together in a supercontinent called Pangaea. Excuse my crude artwork. It looks kind of like a tooth, but I don't know. Pangaea, all of the continents in our great big world in Pangaea. But he didn't just blanket statement out like, oh, Pangaea, all these continents were together. No, he looked at the current science of the day and was taking all of that in and saying, you know what, based on all these different lines of evidence that I see, this could be very probable. And so what we want to do today is not only define continental drift, but here it is, the hypothesis that Earth's continents move across the surface of Earth. but also the 4 lines of evidence that support this idea. So the first is the visual matchup of the continents. Now, when we look at these continents, you could almost smash Africa into South America, smash Europe and Greenland into North America. You could pluck India right off of Asia, swing it around, smash it in here to the bottom of South America, and you could smash. Basically, what I'm saying is that, with maybe too many smashes involved, is that there is a puzzle piece fit of the continents. And again, I mentioned that Alfred Wegener was not he wasn't the first person to ever look at a map and go, huh, you know what, there's a shocking similarity. But what he did do is he took continents like Africa and South America and traced out the continental shelf. Now, continental margins are composed of a shelf, a slope, and a rise before you get to the deep ocean basin. But that point that transitions in angle from the shelf to the slope is the shelf break. And he matched those up and took these 2 continents and could, with great accuracy, connect the continental shelves, the boundary of the continental shelves of continents on opposite sides of the Atlantic Ocean. And so by itself, it's like, wow, that's really something to think about. The east coast of South America and the west coast of Africa fit in really well together. The edges of the continental shelves have a near perfect fit for continents on other sides of the ocean. That's amazing, but in and of itself, meh, okay. So what else? What else we got? Alfred Wegener, what else you got? Rock types, matching geology. And so a little bit of background about the formation of rocks. Rocks crystallize from a melt. This is how we get igneous rocks. A volcano erupts, and that volcanic eruption extrudes lava onto the surface. It cools, minerals form, it creates rocks. Now, the melt that's underneath the ground is going to be a product of the ingredients or the elements of that particular melt. And every volcano is going to erupt a unique mineralogy and create categories of rocks known as igneous rocks, categorized based on the amount of iron, magnesium, and silica relative contents in some of their additional minerals. But each volcano will have a unique eruption. So if a volcano 500 million years ago erupted, it will be unique from a volcano erupting today. If a volcano, let's say, if Mount Lassen in California erupts, it will be different than Mount Fuji erupting. So on and so forth. So with that being said, what we see are rocks on either side of the ocean. We've got rocks over here in North Africa and rocks over here in South America that are the exact same. In fact, these aren't the only places. We've got the same matching rock types of the Appalachians, the Caledonides, the Highlands of Scotland, the Anti-Atlas Range of Morocco. So we've got 4 different places in the world where we have similar rock types. Now, smash all these continents back together, let them drift together, and create these mountains at the same time, and then split them apart. Well, that makes sense based on what we understand for geological processes. What we do not see is 2 independent locations erupting the similar type of rocks, the exact same type of rocks. What we can interpret is 2 locations that have the same type of rocks at one point were together and therefore must have drifted apart. So, line of evidence number 2, matching geologic units, or well, let's say matching geology, geologic units, or rocks. Okay, got it, like that. We've got rocks on opposite sides of the world of the Atlantic Ocean, different continents that maybe could only have been together if they were together in Pangea. So let's go here. We've got rocks. We've got puzzle pieces. What else do we got? What else you got up that sleeve of yours, Mr. Alfred Wegener? Well, Wegener looked at past climates, paleoclimates. And there's a few different indicators. Coal. Coal is a fossil fuel that developed millions of years ago when the Earth was a lot hotter, covered by huge forests. These big forests in a warmer climate around equatorial regions dropped a lot of organic material. And it was wet too. It was hot, it was wet, it was huge forests. Everything from the fossil record indicates this is true. During this period, organic matter formed swamps. Swamps accumulated to develop peat. The peat over time was compressed and transformed into coal. That coal is present all over the world. We've got coal in the eastern US, lots of coal there. Europe, Siberia, Antarctica. How do we have coal in Antarctica? Well, one of the ideas is that Antarctica at one point was near the equator. And so this helps. This helps build the case for continental drift. We're looking at past climates. But not only do we have coal deposits, we also see evidence of, and I believe this is my next slide, evidence of glaciation in Antarctica, in South America, in Africa, in Australia. Have you ever been to Australia? It's hot. The interior of Australia is a big, hot desert with glacial tillites or glacial erratics. They're big boulders that were transported by glaciers that when the glaciers melt just dropped. Also, those glaciers scraped patterns or striations across the landscape, and Wegener was able to map out the direction of these parallel striations radiating outward from Antarctica, because Pangea, it existed from about 299 million to 180 million years ago. That's a long time. That means you could have warm periods, you could have cold periods. And in fact, there were ice ages and interglacials. But the pattern of radial striations moves outward from Antarctica, covering multiple different continents. So past climates, here we're going to have tropical swamps that lead to coal, and we're also going to have glaciers. So two different types of evidence for past climates. That's awesome. But is there more? Tell me, please. Is there more? But yes, there is more. Okay, what else do we got? Fossils. The fourth line of evidence here is going to be fossils. And fossils are what really piqued Alfred Wegener's interest. He started to read about fossils that existed on multiple continents. The Mesosaurus was a freshwater reptile. Fossils of the Mesosaurus found in Africa and South America. Now, you may be asking the question, if South America and Africa were separated by an ocean, how would a freshwater reptile swim across the salty ocean? You would be asking a very good question. Similarly, the Glossopteris, which is a seed fern. memorialized in the fossil record and located on South America, Africa, the island of Madagascar, Antarctica, India, and Australia. So all over the world, we see fossil evidence in the rock record of a plant that definitely wasn't swimming across the ocean. Here we see the Mesosaurus, the fossil evidence of the Glossopteris. So the distribution, the global distribution of fossils that would not be able to cross oceans but are found on multiple continents is another line of evidence for Alfred Wegener's continental drift hypothesis. Now, you are most likely convinced, right? I've got you convinced. The story that I'm telling of how continents drift across the surface of the Earth is compelling, and it's supported with all of this evidence. So this must have been met with high accolades, with widely agreed, and people must have just loved Alfred Wegener, but unfortunately, his ideas were laughed at. The geologic community said, "You're not a geologist. You go to Greenland to study the atmosphere, climate. What the heck do you know about geology?" They also said, "Okay, given all these lines of evidence, tell me how it happens. How do continents move across the surface of the Earth? Or more specifically, what is the mechanism for continental drift?" And that, he had some ideas, but he didn't actually have the right idea. Thought maybe it was the tides and the moon and gravitational forces, but no, the physics there doesn't exactly work out. Well, unfortunately, he died in 1930 before his ideas were ever validated, because they were posthumously. Now we give Wegener credit for the hypothesis of continental drift. He never was able to receive that credit in his lifetime, but here we are over 100 years later, after the publishing of his book, The Origin of Continents and the Oceans, widely celebrating this groundbreaking idea to bring in the 4 lines of evidence. I think I'm on the conclusion. The 4 lines of evidence for continental drift: the puzzle piece fit, matching geologic units, rock types, past climates or paleoclimates, and fossil evidence. Now, we needed this. We needed this idea of continental drift to usher in this new age of plate tectonic theory. Because as we'll see in modern geophysical evidence for plate tectonics, the accompanying lecture to this one, during the 40s and the 50s and the 60s, the evidence for the mechanism which Wegener could not determine at that time became apparent with enhanced technologies and an understanding of the ocean floor. So, thank you for your revolutionary idea that continents move across the surface of the Earth, because it led to the development of plate tectonic theory, which is the unifying theory of geology that states the surface of the Earth is covered by large, rigid tectonic plates. And these tectonic plates move relative to one another, and at their tectonic boundaries, we have earthquakes, volcanoes, mountain building events, and mountain eating events. We have the creation and the destruction of Earth's outermost layer, the crust. Thank you, Alfred Wegener, and thanks to you for your attention. I will see you again.